Welcome back, everyone. In this video, we're going to be looking at the principle of strong induction, which builds upon the previous video which explored the well-ordering principle and the principle of induction. To begin with, we're going to do a brief reminder of what the principle of induction states. So, induction says, suppose that we have a property that we want to show is true for all positive integers at least one. And we can prove this in two steps, including the base case, which is showing that p is true for a small value such as 1, and then the induction step, which is showing that if pk implies pk plus 1, remember this is a domino effect, where we knock down the first domino, and then every domino knocks down the next domino after that, and every domino in the entire track gets knocked down. And the assumption that we make is known as the induction hypothesis. But there's multiple ways that we can strengthen the induction hypothesis, and we'll see that here through two challenging problems that will come up soon. So strong induction instead says, once again, assume that we have a statement P that we want to show is true for all positive integers. We can prove this in two steps. We can again show that it's true for the base case, but then the inductive step is a little stronger, because now we're saying that if k is an arbitrary integer such that all of p1 up to pk are true, then we have to show that pk plus 1 is also true. So as before we had each domino knocking down the next one, now we have all the previous dominoes knocking down the next one. So it's a little bit of a stronger assumption. So I'm going to first off show an example of a problem that can be solved with a regular induction, but with a slightly stronger hypothesis, and then I'm going to show an example of a problem with strong induction. So for the problem with induction with a stronger hypothesis, we're going to look at a USAMO problem here, where we're going to call an integer n good if we can write n as a sum of numbers a1 up to ak, where a1 up to ak are not necessarily distinct positive integers satisfying the sum of the reciprocal numbers are equal to 1. And we're given that the numbers 33 through 73 are good, and we want to prove that every integer greater than or equal to 33 is a good number. So, let's take a look at how we can solve this. And we're going to solve this through two key observations, which we're going to use when we rewrite this equation and multiply it by 1/2. So, again, n is the sum of all the a sub i's. And observe that if n is good, then if we take all the sum of those a sub i's and half them, and then add 2/4 as well, then the sum of the half there plus 2/4 equals 1. But the sum of the denominators in this case is 2 times the sum of all the a sub i's, so that's 2n plus 4, which is 2n plus 8. So we've proved that if n is a good number, then 2n plus 8 is also a good number. Alternatively, we realize that we can also write a half in another way. We can also write it as 1/3 plus 1/6. And in that case, we get 1/2 plus 1/3 plus 1/6. And in this time, the sum of the denominators is now 2n plus 9. So we've seen that if n is good, then 2n plus 8 is good, and 2n plus 9 is good. And this leads us to a slightly stronger form of the induction hypothesis. So we're going to let n be the proposition that n plus 1, n plus 2, all the way up to 2n plus 7 are good numbers. And we see that the base case p33 is actually given here, because we've seen that 33 is good all the way up to 2 times 33 plus 7, which that's going to be 66 plus 7, or 73 is good. So the lower and upper bound exactly match what is given here. So we've seen that this proposition is true, and if this proposition is true, well, if k is good, then 2k plus 8 and 2k plus 9 are also good. So that means that in general, pk implies pk plus 1. Because if k is good, then 2k plus 2 times k plus 1 plus 7 is also good. So all the numbers up to that range are good. So we've now seen that we have the general induction hypothesis is true. So by induction, every integer at least 33 is good. So that's a very tricky problem, but we notice we can solve it with a few lines of a solution here by just strengthening our induction hypothesis. Now we're going to look at a problem that involves strong induction, and we're going to look at it through several examples first. So this comes from a Putnam problem, and it says prove that every positive integer is a sum of one or more numbers of the form 2 to the r times 3 to the s, where no summand divides another. So obviously 1 fits this bill because that's just 2 to the 0th power, 2 fits this bill because 2 is 2 to the 1st power, 3 is 3 to the 1st power, 4 is 2 squared, so all those work. The first interesting number we get to is 5. And 5 is just 2 plus 3, so that works. 7 is 3 plus 4, so that works. 11 is 2 plus 9, so that works. We could also have written it as 3 plus 8. 13 is 4 plus 9, and 17 is 8 plus 9. So we can see that if we double all these representations, we can get all of the even numbers now. So multiplying the terms of these representations by 2, we get 10 is 4 plus 6, 14 is 6 plus 8, and so forth. So doing this process in general, we can use strong induction to prove this is true for every even positive integer. We'll make this argument more rigorous in a couple slides here, but this works for now. So using strong induction, any even integer can be written as the desired sum. But now, what do we do about an odd integer? So to find a representation for an odd number, such as 2001, we find the largest power of 3 less than the number. So we're going to take a very greedy approach and try to find the largest power of 3 that can go into this number and subtract, because we know we're going to be left off with an even number, which is going to help us out a lot. So in this case, 3 to the 6th is equal to 729, which is less than 2001, which is less than 3 to the 7th power. So we're going to subtract off 3 to the 6th power. And we're left off with a remainder of 1,272. So therefore, we must find a representation for 1,272, which is an even number. I'll pause here for a moment and give you the chance to try to do this on your own, and then once you're ready, go on to the next slide and try to see if we can find a representation for 1272 such that it fits this pattern. Well, we'll recall from before we had 2001 is equal to 729 plus 1272. And by the hypothesis, 1272 can be written in the given form. We show that no terms of the sum divide 729 and vice versa. Well, since 1272 is 2 times 636, multiplying this representation of 636 by 2 gives 1 for 1272. Also, since 636 is less than 729, no term of the sum will therefore be divisible by 729. So we've shown that no term in the sum will be divisible by 729, but we don't know if any term in the sum will divide 729. And we can do that easily by making all the terms in the sum even numbers. If we make all the terms in the sum even numbers, well then naturally none of them will divide 729, which is an odd number. So we can further factor out 2, and we're left with 8 times 159, and we continue to do this finding the largest power of 3 strategy. So 159 is 81 plus 78. For 78, we can factor out 2 and get 2 times 39. From 39, we can write that as 27 plus 12, which are both of the desired form. So we get 81 plus 54 plus 24. We now multiply that by 8, and we get all even numbers when we do that, and we get 729 plus 648 plus 432 plus 192 is one representation that works here. So now, let's prove this in general using the principle of strong induction. So the base case of 1 is obvious, because that's 2 to the 0th power. So we assume that every integer up to n can be written in the desired form. We then show that n can also be written in the desired form by breaking it into 2 cases. The first case is if n is even, then n divided by 2 can be written as a sum by hypothesis. So multiplying every term in the sum by 2 gives the desired representation for n. So for example, 5 equals 2 plus 3 and 10 equals 4 plus 6. So that was exactly what we saw before. So the even case is fairly straightforward. Now the odd case is a little bit trickier, but it can be solved by the same greedy strategy that we saw before. So if n is odd, then we can find s such that 3 to the s is less than or equal to n, is less than 3 to the s plus 1. So we basically find the power of 3 that is the greatest power of 3 less than or equal to n. So clearly, if 3 to the s equals n, then we are done, because it's already written in the desired form. So we assume that it's a strict inequality. So if 3 to the s is less than n, then we let n prime be equal to n minus 3 to the s divided by 2. And notice that that is an integer, because n is odd, and 3 to the s is also odd. Now, what can we do with this? Well, since n prime is an integer that is less than n, it can also be written as a sum in the desired form. And we see two things about this. Furthermore, n prime is going to be less than 3 to the s plus 1 minus 3 to the s divided by 2, which is just 3 to the s power. So therefore, none of the terms of the sum of the representation for 2n prime are going to be divisible by 3 to the s. Furthermore, as I mentioned before, all the terms in the representation for 2n prime, because we double all the terms in the representation for n prime, are going to be even numbers. So none of them are going to be dividing 3 to the s plus 1, which is an odd number. So therefore, since they are all even, none of them are going to divide 3 to the s. Putting together the representations for 2n prime, which is just going to be equal to n minus 3 to the s, with 3 to the s, gives a valid representation for n. And that wraps up the first two videos of this course. So, two references here include the textbook Olympian Number Theory Through Challenging Problems and the proof of Alan L. Fry's Proof Without Words of the Sum of Cubes Identity. See you in the next video.